high school.
Sorry, crisis.
But we always got President's Day off. And then when I got here,
we
always got Caesar
I was like,
Chavez
no,
Day.
actually, at that moment I couldn't. Because I could not assess how bad things were.
True, yeah. Yeah. And we had the whole week for Thanksgiving, too.
Yeah, that too.
Which I liked a lot.
Yeah, that was nice. That was cool.
Because usually the Thanksgiving week is the most stressful week of the semester.
Well, because most teachers plan a midterm for that Tuesday or Wednesday.
Well, that's to make sure people come. I mean, I was contemplating doing that too, but for me to still then I realized that it's just people. So
Yeah,
yeah, for the classes I teach.
Yeah, but I mean, normally
like,
you have to go to
no,
school for 3
I've
days, and then you have to
contemplated it, but then
somehow
I'm
get
like,
to your
no,
family
it's just not.
and do the whole thing. It's like,
So,
makes that week
I don't
even
want my
crazier than a regular week, even though it's supposed to be a holiday.
Okay, let's get started. So we left off last time when I showed you guys how to define duality for plane graphs. So here's a graph. Then the dual is putting a red vertex inside each face here. Whenever you see an edge, you connect. Whenever you see an edge dividing two faces, you connect those two vertices with a red edge. So I have some outside vertex here. This is my graph G star. And I stated this theorem that if you take a connected plane graph and if you draw a dual plane graph for it, then the matroid of the dual is the dual of the matroid. In other words, matroid duality equals graph duality in this case. And so we're going to prove that now. So what we need to show is that if I take a basis, so I need to show that what are the bases of this guy, the matroid of G star. So T is a basis of the matroid of the dual. I need to show that the bases are precisely the complements of the basis of M of G. So I need to show that this is true if and only if the complement is a basis of the matroid of G. Okay? This is what I need to show. And remember that for graphs, bases are spanning trees. Spanning tree spanning tree. Okay? So again, there's one nice feature again, which is that we have a self-dual statement. If you take if you prove one direction, then you will have proved the other one by duality. Okay? So let's prove one direction. And actually, to keep the notation clearer, maybe what I will do is that I would always call things. So the red things are going to be in the dual, and they're always going to have stars. Okay? This is the dual. So a red set is a spanning tree if and only if the complement is a black spanning tree. Okay? So okay. So let's assume that T star is a spanning tree of G star. Suppose this, but suppose that that E minus T is not a spanning tree of G. Okay. Remember, what is a spanning tree? A spanning tree is a subgraph that goes to all the vertices, connects everything, and has no cycles. So if you're not a spanning tree, it's because either you don't connect everything or you have cycles. So first, two possibilities. The first possibility is that E minus T has a cycle. Okay. So my black graph has a cycle. E minus. Now, my black graph has a cycle in E minus T. Okay, so these edges are all in E minus T. Okay? I'm assuming this, and because the black graph is a plane graph, that means that it divides the plane into regions. And we know that this is a real cycle. It's a continuous curve, so it has an inside and an outside by the Jordan curve theorem. And so there are regions of the black graph that are inside the cycle, and there are regions that are outside the cycle. At least one of each. So let's take a region which is inside. Let's call it F. And let's take a region which is outside. Let's call it F star. No. If it was F star, then it would be in the dual. Let's call them F1 and F2. Okay. What does this mean? This means, put the labels outside of the faces. F1, F2. I have a red vertex inside each black face. So if I take the dual vertex, F1 star, and if I take the dual vertex, F2 star, then they're going to be like this, right? Now, supposedly T star is a spanning tree, which means that T star connects every pair of vertices. And in particular, T star connects every pair of red vertices because it's a spanning tree of the red graph. So I must have a path, a red path inside T star that goes from here to here. Okay? But again, this curve has an inside and an outside, and so if I want to go from inside to outside, I must cross at a certain point. Okay? But then what happens? If I look at this edge, and let me make clear that the black cycle is supposed to be in E minus T, and the red cycle is supposed to be in T star. Okay? Now, if I give a name E to this edge that I crossed in the cycle, then I know which edge I used to cross from here to here. Because if you remember, the definition of the red edges is that we draw a red edge for each black edge, and the red edge is the only red edge that crosses that black edge. So the only red edge that crosses E is the one that we called E star. That's the only edge that I could have used to cross along E. Okay? And do you see how this is a contradiction? E is in E minus T, because E is in the black cycle, and E star is in T star, because E star is in this red tree that I drew, which means that E is in T. And so I found an element which is in E minus T, and it's in T. Contradiction. So contradiction, and that means that E minus T cannot have a cycle. Okay? Okay, so the other possibility for E minus t not to be a spanning tree is that E minus t does not connect the whole graph. And so let me imagine that my graph is the same one that I drew over there. And if E minus t does not connect all of G, then that means that I can split the vertices into two groups that are not connected. Okay, I can assume that, for example, these vertices over here and these vertices over here are not connected in G.
They may not even be connected
To any.
each other, but you know you can at least find two disconnected pieces.
Right, it could be that this is not connected either.
Yeah.
But I can, I mean, if the graph is disconnected, then I can definitely split it into two pieces that are not connected. So that's what I'm doing. So let's assume that these vertices U and these vertices V are not connected by E minus t. Okay. What does that mean? That any edge from my graph that goes between U and V is missing in E minus t. So let's draw those. I'm going to draw them as dotted lines. I'm missing one, huh?
Yeah, there should be one more. That second to the top guy wasn't there.
So I drew all the edges between U and V, and these edges are all missing in E minus t. Okay. And these guys may or may not be missing. I don't know. Okay. But then let's look at all the faces that are formed between U and V. Okay. So here's one face. Here's a black face, so I have a red vertex. Here's a black face, so I have a red vertex. And so on. And then here's the outside face. Okay. These dotted lines are not in E minus t. And therefore they are in t. Okay. So each one of these guys is in t, and therefore the red edge that crosses it is in t star. So this guy is in t, so this guy is in t star. This guy is in t, so this guy is in t star. This guy is in t, so this guy is in t star. This guy is in t, so this one is in e star. And the one from here to the outside being this one, is also here. So these guys are all in t star. Okay. And that's my contradiction, because I assumed that t star was a spanning tree, and I found that it has a cycle. So therefore, I get a cycle in t star, which is a contradiction. End of proof. Okay.
Can I? So this one, in the first part, I see how sort of the picture, to me, the picture just sort of made clear what the proof was, but it wasn't, the proof stood sort of separate. This one, I don't yet, I mean, I see why it happened here. And I'm confident that if I drew 500 of them, it would happen in all of them. But I don't yet see how I don't yet feel like I have the words to say it separate from the picture as to why that cycle has to occur.
Okay.
I think it's because it's disconnected, so you're always.
So let me just make sure that everybody heard the question. So the question was, in this picture, it's kind of clear how you would write this proof. And in this picture, maybe it's a little less clear how you would write the proof. So you have a suggestion,
I was just
Jameson?
going to say, since it's disconnected, you're probably always going to find two different edges going to that outside guy, right? So you can, which will form some kind of cycle.
I mean, really, yeah. Maybe let me say this proof again a little bit more formally. Okay. I split into two groups of vertices. Okay. Now let's look at the subgraph on each one of those vertices. So here's one of them. Here's the subgraph U. And here's the other one, the subgraph V. When you draw these things, they're going to be blobs in the plane. And they're separate from each other because they're disconnected. So here's one blob. Here's another blob. Okay. Now, if you look at all these cross edges, basically this is going to form a bunch of regions in here. Just again by I mean, one way in which you can think about this is just imagine that you take your pen and you just draw a loop that separates these two blobs, and see what edges you intersected, what black edges you intersected, and that's how you define.
And you're saying that loop has to exist because there has to be a black edge there, so you have to intersect it. Because they're disconnected.
Right. So
at least one edge that should be there.
That connects.
Yeah.
You know, there's one edge from the original graph.
that's a very good point, actually. So let me say that again. So you just draw this red loop, okay? And the question is, how do you know that you cross something in here? I know because G is connected.
And because T star is a spanning tree. So like,
No, but I mean the black graph is connected, and
Right.
because the black graph is connected, I know that these two blobs that are disconnected in E minus T, they are connected in G.
right.
So there must be edges going here. When I draw this loop, I just see which edges I intersected, and those are going to define this cycle for me. Okay.
So when we say T star is the basis of the matroid of G star, does that automatically imply that T is the basis of the matroid of G? Like nowhere out there do we really say what T is, but I'm assuming that it's the dual to G star.
If T star is a basis of G star, that doesn't at all mean that T is a basis of G. But what it means is that, I mean, when I say T star, I mean the red edges corresponding to the black edges T. And maybe I should do that in an example so that's a little bit clearer. So for example, let's say that,
So T is the set of those black edges?
for example, let's say that T is some set, and it consists of edges E, F, and G, where E is this one, F is this one, and G is this one. So this is T. That's T. So the set T star is going to consist of the dual edges to these. E star, F star, G star. So here's my black edge E, and I have exactly one dual edge to it, which is this one. So I call it E star. This is my edge F, so I have exactly one red edge that crosses it, and it's this one, F star. And then this is G, and so I have exactly one red edge crossing it, which is this one, which is G star. So when I say T star, I mean, when I go from T to T star, I basically either add stars or remove stars. Okay? And what we're showing here is exactly that T star is a basis of G if and only if T star is a basis of G star if and only if E minus T is a basis of G. Okay. Eric.
I'm sorry, Federico. Just to touch back on what Kim said, I think that's right. So with the proper treatment so specific, would have ellipses or something between vertices to suggest that maybe there's many more than are actually there. I mean, I saw a proof. I'm not very familiar with proofs in graph theories. Proof I did see in matroid theory by Oxley is that he does generate a graph, but he just makes it very general. So it's not like a finite number. You can't really count all the vertices. Is that kind of the idea that we would impose if we want the picture to accompany the proof?
Yeah, I mean, you'll see that problem 1 of the next homework is precisely about this. And precisely what I'm asking you to do in problem 1 of homework 3 is to formalize statements about duality in graphs. And these are statements where maybe you look at the picture and you'll see it from the picture. And then the point is that to give you guys practice on how you actually formalize what you see in a graph picture. So it's really a little bit of practice on graph theory proofs. I don't want to stop on this for too long because there's other things that I want to say, but I'll be perfectly happy to expand upon this in office hours with any of you guys. Okay. And you'd also have to do it yourself, and I think that's really the best way when you have to do it in the problem set. Any other questions about this proof? So here's a corollary of this. Let's say that G is a connected plane graph. And let's say that V is the number of vertices. E is the number of edges. And F is the number of faces. Then actually there's a relation between these three numbers. V minus E plus F equals 2. Question?
There's still another direction to go on that, isn't there? We did the down direction, or do we already have to
Oh.
the reverse direction?
But by duality.
So I said it too quickly, and I meant to expand on what I said. So let's make a parenthesis here. I'll go back to this, and let's talk about the other direction and how. What's this business about this statement being self-dual? So the thing is, I proved this direction, that T basis of M of G star implies that E minus T is a basis of M of G. Okay? Now let's apply this. Do I have a
T star?
T star? So basis of M of G star implies that E minus T is a basis of M of G. Okay? Now what is E minus T? E minus T is E star minus T star star. And G is G star star. Where here I'm using the fact that G star star is G for G connected. Okay. And then I say, okay, I'm going to use this statement again, but I'm going to use it for these guys. So I'm going to think that this is going to play the role of my T, and this is going to play the role of my G. Okay. So if I call this 1, then by 1, which we already proved, this implies that here I had t star and I went to e minus t. So here I had e star minus t star. So I have to go to e star minus t star. And here I went from G star to G. So from G star star, I would go to G star. Okay. And E star minus T star is T star. So applying 1, I actually get exactly what I wanted. E minus T basis of M of G implies T star basis of M of G star, which is the converse. Okay. So this is what I mean when I say that one direction is dual to the other one, because one direction, I prove it. And then if I apply this direction to the dual matroid, then I get the other direction, to the dual graph. Okay. In other words, these two directions are logically equivalent, and if I prove one, I prove the other one. So this is the second direction of the proof. Okay, so corollary of the statement about duality in planar graphs. I'm claiming that a corollary is this formula. I'm sure that many of you have seen this formula before. People know this as Euler's formula. So Euler proved this. Maybe you've seen it for graphs on the plane. Maybe you've seen it for polytopes. So if you have a three-dimensional polytope, three-dimensional polyhedron, and if you take the number of vertices minus the number of edges plus the number of faces, you get 2. And this is the proof. If you take a polytope, you can draw it on the plane, and then apply this theorem. Okay. And the way that people normally prove this theorem is through some induction or something like this. But we're going to get a really nice, short, conceptual proof of this. Why? Because remember, how many? We talked about this. If I take a connected graph, G connected, then a spanning tree of G has how many edges? Well, if you have 7 vertices, then you need to connect 1 of them, 2 of them, 3 of them, 4 of them, 5 of them, 6 of them. Every edge connects 2 vertices that are not connected. So any spanning tree is going to have v minus 1 edges. Okay. So for G, a spanning tree has v minus 1 edges. But this is also true for G star. For G star, a spanning tree has v star minus 1 edges, where v star is the number of vertices of G star. V star is number of vertices of G star. But remember that we have a vertex of G star for each face of G. So this is the number of faces of G. So V star minus 1 is really the number of faces of G minus 1. But we saw that a spanning tree of G corresponds to a complement of a spanning tree of G star. So if this guy has V minus 1 edges, then if I have something here T, then here I have E minus T star. So if this guy has V minus 1 edges, then it has E minus this number of edges. So because T is a tree of T is a spanning tree of G if and only if E minus T is a spanning tree of G. That means that the number of guys here is, because it's a spanning tree of G, is v minus 1. But because it's E minus a spanning tree of G star, the number of edges is E minus F minus 1. And I'm done. Here's my proof.
Is that a little equal sign between the two lines, or is that a double arrow there?
This is an if and only if. If and only if. And V star minus 1 equals F minus 1. Okay. So that's nice. So that in a way explains why Euler's formula, and it gives a good conceptual reason why it's true. Any questions about it? I think any of you who have actually had to prove this formula before must really appreciate this argument, because this is a formula that is pretty annoying to prove by hand. You really have to kind of get your hands dirty and say, you know, what happens if I add a vertex or if I add an edge or something like this. And here it just comes out from the theory. I want to show you something that I'm not sure whether you've realized this or not, which is that a graph might have different duals. What do I mean by this? I mean that if you take an abstract graph and if you draw it in two different ways, then that might give you completely different pictures for the dual. So for example, let's consider this graph. Okay. Here I drew it in one way, and here I can draw it in a different way. Okay, these are clearly the same graph. But now let's draw the dual of each picture. So here are two realizations, two drawings. Remember, people also call this embeddings of the same graph. Here's one. Here's another one. They're the same graph, and now let's draw the duals. Okay, so dual let's see how I can draw this in a way that you can kind of see what the graph looks like. So let's put a vertex down here, one here, here, and here. One vertex in each region. Okay, so I connect these two. I connect these two. This guy is connected in two ways to this one. This guy is connected in two ways to this one, and this guy is connected to this guy.
What about the coming out?
Am I missing something?
Straight up.
Edge.
Oh yeah, the easiest one, this one. So this is G1 star, and let me draw it a little bit nicer so that you can see what it actually looks like. So here are the four vertices. I have this, I have this, I have this. Then I have a double edge from here to here. I have a double edge from here to here. And then I have this edge going around. Okay, so this is what G1 star looks like. Okay, what happens if I take the dual of G2? And draw it like this. So here I have, let's see, these two guys, these two faces are connected by this edge and by this edge. This guy is also connected to the outside one. This guy's connected to the outside one over here and over here. These two are connected. And this guy's connected like this and like this. And again, so this is G2 star. Let me draw it again. So it goes like this, it goes like this. Here I have a double edge. Here I have a double edge. From here to here I have a single edge, and then I have one going around. So this is G2 star. Okay? Now, okay, so these two look different, but are they different? Or is it just that I drew them incorrectly, but I can redraw this one to make it look like this, or are these two graphs actually different from each other combinatorially?
Well, on the first one vertex has
They are different. They are different because if I look at this vertex right here, it has the property that there's these two double edges coming out of it. And here, no, actually here that's true also.
Right.
It has six edges coming into it though.
So I'll get to that, but for the first thing, notice that even though this guy has two double edges coming out of here, and here it doesn't look like this one does, it actually this guy also has a double edge coming here and a double edge like this.
But that one has three double edges because it also has.
Oh, but this one has a third double edge, right?
Right.
Yeah.
And this one doesn't have a third double edge.
Yeah.
But maybe it's easier to see that this guy has degree 6. In other words, there's 6 edges coming out of that vertex, and this guy doesn't have any vertices of degree 6. No vertex of degree 6. In other words, two drawings of the same graph can give you completely different duals.
That's weird.
That is weird, and there's a real reason why this is weird, which is that we just saw that these two graphs are different, but we just proved that they have the same matroid. I mean, the matroid of G1 star is the matroid of this graph dual. The matroid of G2 star is also the dual of the matroid I started with. These two are different pictures, but they have the same matroid. So when I dualize, I get two pictures that are honestly different graphs that have the same matroid. And this goes back to one of the questions that someone asked in the forum. Can you construct graphs that have the same matroid even though they are different? Well, here we see a huge way of constructing many examples. Take any big graph, draw it in 10 different ways, and you're certainly going to get 10 different duals that have the same matroid. Not certainly, but you're probably going to get several different. Different pictures are likely to give you different graphs. And so G1 star, G2 star different, but they have the same matroid. Right? This is just the matroid of G dual. In other words, there can be many graphs, many different graphs with isomorphic matroids. Okay. Okay. Now, question, Eric.
A naive question. I mean, clearly G1 and G1 star and G2 star are non-isomorphic. So we can have non-isomorphic graphs that give us isomorphic matroid.
Mm-hmm.
Is there a similar happening within representable matroid?
Yes. So it's definitely possible that you could have completely different vector configurations that will also give you the same matroid. I think after the last homework, you guys will appreciate the point that it's kind of difficult to tell if two matrices are the same one or not. Took you guys a lot of work, right? I mean, this is a hard question. How can you tell if two matrices are the same or not? And this gives us a very natural question. When do two graphs have the same matroid? I don't know what you guys think about this question. I don't know if you think it's an easy question or if it's an open problem that no one would know, or that. That's a very good question. So what happens if you have a graph that only really has one way of drawing it?
One plane.
First of all, does that exist?
Yeah. Do they exist?
Do you have a graph such that all the pictures really look the same?
Triangle. Sure.
For example, a triangle, a square. Okay. So then the question is the dual unique? Or is the matroid unique? There's many questions you could ask, and they kind of come down to this question really. How can you represent a matroid as a bunch of different graphs? Are there different ways, or is there only one way? Well, it turns out actually that this is completely understood, and this is kind of an amazing theorem. It's an amazing theorem that we can look at two graphs, and there is an algorithm to say either they have the same matroid or they don't have the same matroid. And that algorithm is not compute the matroid and see if it's the same. There really is a way of telling.
When was that?
Description, and this is, I'm not sure how old it is, but this is called Whitney's
30s, 40s. So Whitney did it?
Isomorphism theorem, and that means that it can't be too new.
Yeah.
Whitney is one of the fathers of the theory. And I think this would be a and then question. How, and this is really basically just Deep's question, is how are the different duals related to each other? Or is there only one? Or question, how are the different duals related to each other?
Wait, what different dual? Oh, the different
Of a single graph. How are the different duals of a graph of a plane graph related. And actually, let me make it right here planar. Which you may or may not realize is a much harder question.
Well, because then you're saying you could have different drawings.
Well, actually, no, that's not really a harder question.
That's the question you
That
want.
is the question.
Well, yeah,
Because
that's
the question
you
is-
want, but
There
you
aren't,
could-
there aren't different duals of a plane graph,
you
which
just
once it's
have-
drawn is a dual.
It's drawn, yeah.
What,
Yeah.
how are the different duals of a planar graph, in other words, with all the different embeddings of it, with all the different plane graphs that you can make of it? How can you relate the dual pictures? How are the different duals of a planar graph related to each other? Well, Whitney tells you something. Whitney tells you they have the same matroid, so something happens. Okay. But can you say more? And I think this is a good subject for one of the projects that you guys can do. So this could be because I don't think we're going to cover this theorem in the class, but this is a possible project.
Is it in the book, Loxley's book?
It is, yeah. A good possible project. To understand this and see what you can say about it. I actually have a minute, and I can tell you what Whitney says. I can very quickly tell you what Whitney says. There's 3 operations that you could do to a graph. One, say it's disconnected. So it has 2 pieces. So you're going to connect it. You're going to connect it at a vertex.
So you glue them together.
You glue them together by identifying one vertex here and one vertex here.
So you add no edges.
You add no edges. You add no cycles. So if you add no cycles, that means you have the same matrix. The second operation is the opposite. If you have 2 groups and they're connected at a vertex, then you just split them. This doesn't change the matroid either, of course. And the third operation is a little bit more interesting. It says, let's say that you have 2 pieces that are connected. Actually, I just remember that this is called Whitney's 2 isomorphism theorem. You're going to take two pieces that are connected at 2 vertices only. And those vertices are joined by an edge. And then here's G1. And here's G2. So what can you do? What you can do is keep G1 where it is and flip G2.
What do you mean flip?
So now it looks like like that.
Change the identification of those 2 vertices.
Oh, you switch.
You just
okay.
you just change the edge. You basically kind of change the edge orientation, and you get a new graph. Okay? You're not really forming any new cycles either. Think about it, and you see why not. Okay? So this doesn't really change the matroid either. It's easy to see. Whitney's theorem says that this is it.
Those are the different types of.
This is it. So if two graphs have the same matroid, then it's because you just applied a bunch of these operations, and you started with one and you got the other one. I think this is an amazing theorem. I mean, there's no way that you should expect such a simple answer. And so the project will be to understand this theorem, and for example, to see how, by drawing different duals, and if you take a graph, you draw one dual, you draw a different dual. Well, these 2 graphs are supposed to have the same matroid. So how do you use these flips to get from one to the other one?
Deal with disconnected planar graphs now too.
And for example, this means you never care about disconnected graphs, because it's the same thing if you join them at a vertex. All right, stop there. Don't forget to turn in your homework.
back right now, but I'm really hungry. I think I'm gonna go tell them that I.
Would you like to go grab some, or you can go?
No, I'm gonna go check in with Becky.
Let me tag along. I'll go upstairs.
Sure. Have a great class. Think house, not matroid. It's a think house, not matroid.
I saw this great picture of Steve in India, in his office. It's just a really nice picture. Yeah, you just put it up, because, you know,
Oh, no, I was
it's
just
number
gonna ask
eight.
if you're gonna work on
No,
it.
it's,
Listen, this is a good question.
oh, oh, I thought it was from India.
No. That was last year's picture.
Okay.
Yeah.
But it's nice, it's really nice, yeah. Thank you, sir.
It's almost over.
Yeah, well, email me. Yeah.
Needs lots of work.
You type it up in LaTeX like she did. Still have time.
Thanks.
My office, but that's okay.
Maybe after the health session.